Hello everyone, Harvey here. This is just a quick video demonstrating how I determine the calculations for the Rosemary Ainslie circuit that Glenn, aka FuzzyTomCat, did with his 520 volt run. This is file number 40 microseconds underscore 520 volts underscore 10 underscore 5 underscore 9 XLR. And real quick, we have our timestamp down the left column, so for any given period within the sample you can see how much time has passed between the samples. It doesn't carry out that many digits, so you can see that you just have a very small variant between them. Let's see, what else was it? Oh, also it's negative all the way up to about I think it's line 4,000, somewhere around there. 4,000, yeah, here we go, 4,992. So that's probably the center mark, at the center of the scope. And for the calculations, we have the shunt watts, column B squared over the resistance, which we know is a 3% 0.25 ohm resistor. So this is our power, standard equation, E squared over R. What is column B? Column B is our shunt. That's channel 1 is put right on the source. The other side of the shunt is at the B minus, so this represents the voltage drop across that resistor, which gives us the current that's flowing into the battery on the negative terminal. Our load watts is a little more complex. Here we have to take the battery voltage, which is monitored on channel 4, and we subtract the drain voltage, and that gives us the voltage drop across the load resistor. Okay, so we have the voltage drop across the load as E2 minus C2, that's in parentheses, and then we square that over R. Our load resistor is 10 ohms. So this gives us our load watts. Now I want to stress the point, as I mentioned in the forum, that this is a wattage that's determined by the ohmic treatment of these values. It does not take into consideration any phase shift between the voltage and the current. And we know there's going to be a phase shift there because this is an inductive resistor. There's inductance there. There's also capacitance there. And so we know that the current through that device is not truly in phase with the voltage for that device. That means the power is going to be less than what we've determined ohmically. The only real way to know is to get the temperature readings, and that's why the temperature is so important in this process, because then we don't have to concern ourselves with that phase shift or how much of a phase shift there is because of the capacitance involved, which negates the inductive phase shift, and they cancel each other out and all that stuff. And so trying to figure out how much current is present at that instant in time. So these are just, your load watts here is just a general reference just to get a feel for what's happening if it was truly an ohmic situation. I also include the shunt current, very easy, voltage drop across the shunt. Load current, same principle as before. We determine the voltage across the load, divide that by 10. Our battery watts, very easy again. We know how much current is flowing into the battery because that's what's going through the shunt resistor. So how much power is that? We simply take the battery voltage at that instant in time times the current that's flowing through there, and that gives us our battery watts. So you'll see our shunt current, H is our shunt current, times E2, which is our battery voltage, gives us our battery watts. Pressing the end key on my keyboard, going to the bottom, we find that these are our averages, and we'll see that our battery watts has a negative average. We'll also see, by the way, that the formula for that is simply the standard average function for that particular column. And then we trying to change my formula there. And then we have the minimum. Again, it's just a standard function in Excel that finds the cell that has the lowest value, and then the maximum, again a function in Excel, gives us the positive value. So all combined, we have all of the averages for each one of these columns, all the minimums for each one of these columns, and all the maximums for each of these columns. And I've posted this data in the forum so that you can do this analysis yourself and compare it and see that the battery watts at a particular instant in time is a true wattage, because here we have on the shunt, we have a negative voltage drop across that. That means we have a negative current flowing through the shunt. If we have a negative current flowing through the shunt, and we have a 44 volt potential on the battery, then that power is this times this, and that's what we have there, negative wattage of 190 watts. Okay, so I hope that clears that up. Hopefully this sample run that Glenn did for us is a forebearer of a future run where we can really do a good analysis, maybe get a spreadsheet dump every half hour or so during the 7-hour run, or however long he wants to do it, and maybe some temperature analysis every 15 minutes, something like that, to go along with it, and then we'll have some real data that we can crunch. There we go.